All right, hello there. So in class, we got the first page done. We were doing tangent planes. What the? Hang on a second. All right, there we go. So equation of a tangent plane there. We found some tangent planes, and we had linear approximation and linearization. Make sure that this guy right here, there was an error when we were in class. This is supposed to be 256 for that 4, -8. But again, you don't have to really do that. You can just find these two numbers right there, and then anybody can find the z. Apparently, not me. All right, so let's get back to where we left off. So what we just learned from this last example right here is that basically when you do this linear approximation, it's basically close to the real answer of plugging in the numbers into the problem. And so we just learned that a linear function whose graph is this tangent plane, all right, we're going to turn this into our L of xy, which is called our linearization of your function at AB. Okay, so what we're going to do is move this over here. So basically that Z0 is the answer you get when you plug the A and the B into your problem, right? So like when we did that here, that was the 12. It was already given to you here, but if you plug in 1 and 3 into this problem right here, you get 12. And so that's what is going to be moved to the other side. So Z0 is really also called f of AB. It's a function's value at AB. All right, and then we're going to write the rest. So plus, we're going to have fx times x minus a, because a is the point, the coordinate that we're using, and then plus fy times y minus b, because remember a and b are the numbers you're using to plug in. All right, and so if we say L of xy, that's called the linearization of the function at AB, and if you change that to f of xy, that is called your linear approximation of the tangent plane approximation of your function at AB. So let's go ahead and do that down here. So to do this linearization, I need fx and fy. So when I do fx, I have a 1/2 power, so a square root, so I have 1/2. I put the center back, x plus e to the 4y, and then take 1 away, so minus 1/2. Then I'm multiplying by the derivative of the inside part with respect to x. So the derivative of that x right there is 1. And so I'm going to have to actually plug in, so at 3, 0. So if I plug 3 and 0 into here, I end up getting 1/2, 3 plus e to the 0, so 3 plus 1 is 4 to the negative 1/2, and then times 1. So that's 1/2 times 1/2 times 1, so that would be 1/4. All right, fy, so start off the same way, 1/2, x plus e to the 4y, the negative 1/2. Now I have to do the derivative of the inside with respect to y, so the x goes away, my e to the 4y, the derivative will be e to the 4y times 4. All right, and we're going to have to do this at 3, 0. So let's go ahead and do that. If I plug 3 and 0, I get the same thing in the beginning here. So I get 1/2, 4 to the negative 1/2. But now it's times 4, e to the 4 times 0, so e to the 0 is 1. All right, so basically I have my old answer that I had before, but now it's times 4, so my answer is 1. All right, so now I need the answer for this. I need 3, 0. I need f of, so I need to find this part right here, f of AB. So if I put 3 and 0 back in my original problem right there, I have 3 plus e to the 0, so 3 plus 1 is 4. The square root of 4 is 2, so 3, 0, 2. So here's my linearization, 3, 0. It's going to be 2 plus 1/4 x minus 3, because we're using the x value of 3. Let's see, plus 1, because that's my slope down here. These are my slopes I'm using. And then I have y minus 0. All right, and so we clean that up. We will get 1/4 x plus y plus 5/4 when you clean that all up. So that's your linearization at 3, 0. All right. So sometimes it's difficult to tell whether a function is differentiable at a point because we first have to check if it's continuous, and to check if it's continuous, we got to see if the limits exist. And so this is a whole big pain, you know, just like we did in a section ago there. And so instead, this theorem down below says if the partial derivatives fx and fy exist near AB and are continuous at AB, then the function is differentiable at AB. So really that's going to stop us from having much problem at all. So in this next example, let's show that this is differentiable at 1, 0 and find its linearization. All right, so basically you go ahead and do the derivatives. So the derivative of x e to the xy, there's an x in both, so I have to do a product rule. So derivative of x is 1 times e to the xy, plus the derivative of e to the xy would be e to the xy, but times the derivative of xy with respect to x, so it would be y, times the original x that's already there. All right, so then I have fy, so basically I can ignore that x in front, just leave it there. The derivative of e to the xy is e to the xy times another x, because the derivative of xy with respect to y is x. So I end up getting x squared e to the xy. All right, so if I look at these functions right here, so if I look at this guy and that guy, there's no holes anywhere, there's no problems plugging any number I want in for x and y anywhere. I can plug anything I want in there. There's no x's in the denominator or something like that, which would make me say, oh, this function doesn't exist at 0, that kind of stuff. So there's no problems, so we can tell that it is differentiable because of this guy, this rule right here, okay? So now we want to actually go ahead and see at the point we're talking about at 1, 0. So at 1, 0, this thing is going to come out to 1 because I end up getting e to the 0 plus e to the 0 times 0 times 1. And this guy down here, I end up at 1, 0. I end up getting 1 squared times e to the 0, so that's 1 also. All right. So we're trying to do our linearization. So we want linearization of 1, 0. I need f of 1, 0, so I got to plug 1, 0 back into my problem. So my function, so I have 1 times e to the 0, which is 1 times 1, which is 1. So I got 1 plus my derivative with respect to x is 1, and then I got to do x minus 1. So many ones. Plus the derivative with respect to y was 1, and then y minus 0. All right, and so when I work that all out, you get an x plus a y, and the other ones cancel, so you have x plus y. All right, so what you have found right here is that your linearization at 1, 0. So when you're close to the point 1, 0, you can approximate the function by adding the x and the y. All right, so if you want to approximate this function at 1.1 and negative 0.1, you can say it is approximately the addition of the x and the y. So it's approximately 1.1 plus negative 0.1. So that would be 1. Oh, yay, 1 again. All right, and actually, if you go ahead and plug in those numbers, I don't have it on there. You don't have to. Never mind. All right, so what we're saying right here is that x e to the xy is approximately x plus y when you are near the point 1, 0. So it's not x plus y everywhere. It's just x plus y when you're near the point 1, 0. Okay? All right. So differentials. So I don't know if you remember, you did differentials last year. You might not remember, but if you just look at what we have here, then you'll be fine. So differentials, some things here. For a differentiable function, you define the differential dx to be an independent variable. Dx is can be given the value of any real number. The differential is then defined as the differential of y is dy equals f prime of x dx. All right, so they were doing like the derivative of that guy right there. Okay, So when you do differentials, you have a couple things. You have dy. So dy is going to be the amount that the derivative changes, the amount that the tangent line changes. So basically when you're at your new spot, it's the distance of the y. Like you were here and you've gone to here, so like you've changed that much with dy. And then delta y is going to be the amount that the function changes. So this blue thing, how much does it change when you're at your spot and then you're at the function's value changing right there. So it's the change in the tangent line versus the change in the function itself. So those are those two pieces right there. All right, so really you don't need to get that necessarily, but here is what our formula is going to be. So dz, when we have three variables, dz is going to be fx of xy times dx, fy of xy times dy. So we're going to kind of abbreviate that. We're going to be doing dz dx, so the derivative of z with respect to x, which is what fx is, and then we're multiplying that by dx, the change in x. All right, and then we're going to say dz dy times a change in y. And I know it looks like you can cancel the dy's and the dx's, but watch what we do on the next page. So this is just the whole same picture in 3D. And so notice you got the change in the tangent plane versus the change in the actual function. So here we go. So in this example, you have your function, find the differential dz. So to find that, we of course need fx, we need fy. And fx is going to be 2x. The 3xy, the derivative with respect to x will be 3y. And the derivative with respect to x of the y squared is just going to be nothing. Fy, the x squared is nothing. The derivative of 3xy will be 3x minus 2y then. All right, so dz is 2x plus 3y, that's this guy, times dx plus then this guy, 3x minus 2y times dy. Okay, so let's actually use this for a purpose here. If x changes from 2.2 to 2.05, so that change right there is up by 0.05. And then y changes from 3 to negative to 2.96, so that change is negative 0.04. So what we're going to do, so compare the values of delta z and dz. So dz we're going to get, because we have our formula in part A. So dz is this. So this is how much the dz is how much the tangent plane is changing right there. Okay. All right. So 2x plus 3y. So I need 2 times my x is 2 plus 3 times my y is 3. So I'm using these numbers right here. And then my change, my dx, my change in x is 2 to 2.05, so it's 0.05. Plus, then I have 3x minus 2y, so 3 times 2 minus 2 times 3. So that's going to be 0, right? Times dy, so the change in y is negative 0.04. So calculate that out, and you get that dz is 0.65. Okay, so that is your change in your tangent plane. Okay, so let's see, if we wanted to find the actual change in the function, we would have to do a little bit longer calculation. So the change in the function is going to be your new spot, f of 2.05, comma 2.96, minus your old spot, f of 2.3. All right, so if you do that, you know, plug 2.05 and 2.96 into your function, then plug in 2 and 3 into your function. I'm just going to go ahead and tell you that the answer is 0.6449. So that is very close, right? That's close to what we got right here. So it's just approximating. So the tangent plane the change in the plane can approximate the change in the function, okay? And I would assume as long as you just don't go too far away from it, you know, like that was a small change and a small change, I mean, if you're going to go really far away, then, probably not going to be that good. All right, so down here, we're going to use differentials here to calculate, estimate the maximum error that we're going to get when we measure. So you measure something and, you don't measure it too well. How much could that affect the measurement of, say, like the volume of this little elephant hot tub here? So a circular spa or hot tub is 7 feet in diameter. So that means my radius is 3.5 feet and 3 feet deep. So my height is 3 feet. And if the measurements are accurate to within 0.05 feet. All right, so what I'm doing here is I'm trying to use differentials to estimate the maximum error in the calculating the volume. So the volume of a cylinder is pi r squared, the area of a base, times the height. Okay, so we have to come up with our differentials here. So I have two variables, r and h. So I got to find VR and VH, my derivatives, right? Because those are what go like right here and right here. All right, so the derivative with respect to r will be 2 pi r, and then h goes back. The derivative with respect to h is going to be pi r squared. All right, so my dv, because my equation is equal to v, is going to be 2 pi rh times my change in my radius, so dr, plus pi r squared times my change in my height, so dh. Well, both of those changes were 0.05. Those are like the amount off I was going to be, or I could be. So I got 2 pi, r is 3.5, h is 3, dr is 0.05, plus pi r squared, so 3.5 squared times, d and h, or no, it's dh, sorry, 0.05. Right, so calculate that out. You get 3.85 feet cubed. So your volume is off by 3 cubic feet. Well, that doesn't mean that much to you. Why don't we actually find the volume of what we, of this little spa or whatever. So the pi r squared h, so pi, my radius 3.5 squared, and h is 3. Because like, unless I know the real volume, I don't know how much I care about this 3.85 business. All right, so if I calculate that out, you end up getting 115.5 feet cubed. All right, so if you're okay, if your volume is about 115.5 feet cubed, and your measurements are within 0.05, like because you're trying to make, how much water's in there or whatever, the volume that's in there. If your measurements are that close, then you're going to be within 3. So that seems pretty good, right? Like 115, give or take 3. So, or probably give or take half of that. So, so it seems fine. Okay. Like how much error are you willing to have? All right, this last couple right here, we're going to do this one in class, but let's do this one up top. So the dimensions of a closed rectangular box are measured as 80 by 60 by 50. So that's going to be our length, our width, and our height. All right, closed box. Possible error in measurement of 0.2 centimeters. Okay, all have the same units. So use differentials to estimate the largest possible error when the volume of the box is calculated from these measurements. So my volume formula is length times width times height. So I have to do my dV is going to be the derivative with respect to L, so that would be WH times DL, right? And then plus my derivative with respect to W, which would be LH times dW, plus my derivative with respect to H, so that would be LW times, what was H, so DH. Okay, so the DL, the DW, and DH are all possible error 0.2, so it has to fill in these numbers, my width and my height. So that'd be 60 times 50. So let's see, 60 times 50, that's going to be 300, and then DL is 0.2. All right, and then L times H, so 80 times 50, 8 times 5 is 40, so it's going to be 400, right? 8 times 5, 40, 2 zeros, yeah, 400. DW is 0.2 again, and that was LH, and so now I need LW, 8 times 60, so 48 with 2 Oh, wait a minute. Oh my gosh, I'm sorry. Oh God, it's late. Let's see, W times H. W times H, so 5 times 6 would be 30, and there's 2 zeros. So that would be 3,000. I bet you were like, what? All right, L times H. So I got 80 times 50, so it's 40 with 2 zeros, so it's 4,000. And then finally, L times W, I got 80 times 60, so it's 48 with 2 zeros, so 4,800. Or just put in your calculator, right? All right, so this is 2,360 centimeters cubed. And you're like, whoa, that's a big error right there. Well, the volume of this thing, length times width times height, is 80 times 60 times 50. That is 240,000, this is in centimeters, that's why it's so big, centimeters cubed. So when you take a look at that, you're like, oh, well, 240,000, what's 2,360? So at least in my mind. All right, so we're going to do this last one in class next time, and you will not be doing, I think I took 19 off your list right there, but I'll see you in class. You'll be doing these problems in class. All right.